Hi everybody. So I hope you can hear me over the sound of the air blowing in my classroom. As you know, it's kind of crazy in here. So we're going to switch over to the lecture notes from what's going to be our new book when they eventually all come in, because I like these notes a little bit better. They're Even though they're not as narrative as the notes we've been doing, I feel like they're a little bit more informative and kind of feel like that's more valuable. So we're going to look at chapter 1. These are basic concepts, which is just kind of the background, maps, geography, what are maps, where do maps come from, what are the important things we need to know about maps, background, blah, blah, blah. Okay, so our key issues are how do geographers describe where things are, why is each point on Earth unique, why are different places similar, why are some human actions not sustainable. We have lots of learning outcomes, Okay, so first of all, just in case you weren't quite sure and I didn't specify, geography is the study of where things are found on Earth's surface and the reason for the locations. Human geographers ask two simple questions. Where are people and activities found on Earth, and why are they found there? So, that being said, a map is a two-dimensional or flat scale model of Earth's surface or a portion of it. And cartography is the science of map making. So, FYI, a map is geography's most important tool for thinking spatially about the distribution of features across Earth, and cartography is the science of map making. So what we have been doing in class, as we've been tromping back and forth across the football field and then measuring the learning cottages, is cartography. Now, maps themselves serve two purposes, and these purposes are as reference tools and as communications tools. So as reference tools, they identify objects' absolute, and remember, absolute location is their longitude and latitude. So absolute location is, a pinpoint on a map. There's no question. When you have the longitude and latitude, you have the very specific degrees down to the minute and the second, and there's no question where that object or that place is. Then the relative location is where it is relative to. So is it southwest of this place? Is it north of this place? So it's its relative location. And then the map is also a communication tool to convey the distribution of human activities or physical features. So you can communicate, this is where these humans have migrated from this place to this place. This is where this population is. This is where we have lots of coal mining. This is where we have so many Christians versus this many Jewish people. Physical features, so we have a mountain range, a river, blah, 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 blah. So the earliest maps were reference tools. These were navigation devices. They are showing people how to get from point A to point B. And the first map was prepared by Eratosthenes, I think I said that right, who lived a very long time ago. And then improvements were made upon his map by Ptolemy. And after Ptolemy, advances in cartography were primarily made by the Chinese and people in the Islamic world. And then map making isn't going to really be revived until during the Age of Exploration and Discovery, when we have lots of Europeans out there trying to find ways to get to Asia by sea, and so they're going to be making all kinds of different maps. So this actually is really cool. If you were in AP World History, you may have seen this map before. So this map shows the different currents. So I believe these are islands here, and then the different currents in the water are marked by these kind of reed pieces, which is very neat. So this is one of the oldest maps. And then here's a map by Eratosthenes. So we have Asia, India, Europe, Libya is quite large. So and here's Arabia down here, the Atlantic Ocean, the Northern Ocean. So that's pretty darn cool. And then we have, I'm guessing this is a map by Ptolemy, a Roman map. Okay, so contemporary map making, maps are going to shift from being simply a tool that provides a location reference to one that actually communicates complex geographic phenomena. So it's going to tell us a lot more than just where things are located, but more demographic information, economic information, and physical information. So the level of detail and the amount of area covered on the map depends on its map scale. And that's what we've been dealing with when we've been making our maps is, the amount of steps you took and the length of your step versus the size of your paper. And so the scale you have to make your buildings in order to fit them on the paper. So the scale is the relationship of the feature's size on a map to its actual size on Earth. So map scale is presented in 3 ways. Okay, first it can be ratio or fraction scale. And that can be shown as a ratio 1 to 24,000 or 1 divided by 24,000. So the number on the left is 1 unit of distance, while the number on the right represents the same unit of distance on Earth's surface. So for example, 1 inch might be 24,000 inches, or 1 foot, well, no, that wouldn't be logical. 1 inch would be 24,000 inches. Whereas, on our transverse maps, we were doing 1 inch would equal 3 inches. Is that what we said? 1 inch was 3 feet. 1 inch was 3 feet. Is that correct? Okay, then you can also have a written scale. And these we see a lot. Oh, no, I lied. We usually see a graphic scale. A written scale, 1 inch equals 1 mile. So the number on the left is the unit of distance, while the number on the right represents a different unit of distance on the Earth's surface. So 1 inch equals 1 mile. And then the graphic scale is what we generally see. It usually consists of a bar line to show the distance on the Earth's surface. It shows the distance between 2 points, and it can be overlaid on the scale bar to determine the distance on the Earth's surface. So usually you can take either a straight edge or a ruler, hold it up to that bar line and say, okay, if I have this much space, I can hold that up to my map and say, this distance is 500 miles, or this distance is 1,000 miles. So these are some different scales. I'm sorry this is very tiny. I'm not quite sure. They could have fit these on here, I think. It made them a little bit bigger. But you can see up here, this is the graphic scale. So up here you see you've got this distance right here, maybe centimeter, that's 20 miles. So you pop it up here, you're like, oh, this distance is 20 miles, okay. And then you go down here, this distance now is 5 miles. So 5 miles. And then they also are showing you the ratio scale. Ratio scale. So 1 is 10 million. And then you can see down here, whereas this is miles, this is feet. So this is, this bit here, about a centimeter, is 2,000 feet. And then down here we have 200 feet, which makes more sense because the scale is going to be much more zoomed in, because here you can, just see the landforms. Here you can start to see the roads. Here you can really see the streets, and here you can see the baseball diamond, the Minute Maid Park. So here we've got Southeast Texas, Houston itself, the city, Central Houston, so a region of the city, and then very specifically the baseball field, baseball diamond. Okay, so the scientific method of transferring locations on Earth's surface to a flat map is called projection. And that's important to know because obviously, hold on a second, I'm trying to do the timer on my phone and I don't want it to emergency dial people. Okay, that's important to know because clearly the Earth is a sphere and we want to make, a map on a flat surface. So there's going to be some distortion there. We can't make things, you can't take the earth and just like skin it and make it perfectly work. So these types of distortion, one, the shape of an area is going to be distorted. Two, the distance between points may become increased or decreased. And three, the relative size of different areas can be altered. And four, the direction between points can be distorted. So that being said, when you come in tomorrow, take a peek at the map that's on the wall where the projector screen is. And you'll notice that map has a different type of distortion than maps you're used to seeing. It tries to show a different version of distortion than we're generally used to seeing. And what it tries to do is kind of take a non-Eurocentric point of view, because generally we're used to seeing Europe and the United States, or the Americas at least, very large, and this map does not do that, and you'll notice that Africa is very large on this map. Okay, so there are different types of projection, and we have Mercator projection, which makes everything into a square, and we see these a lot because when you pull a map down, that's easy to make. And then we have the good Homolocene projection. These are challenging, but look how nice everything looks on there. And this does look very much like you've skinned a globe. And then we have the Robinson projection. And this is the one you're probably very used to seeing in your textbook or when a map is pulled down, because everything is on there, everything is kind of rounded out the way you normally see it, in school at least. Okay, so a map has a geographic grid, or a geographic grid is a system of imaginary arcs drawn in a grid pattern on the Earth's surface. And meridians are arcs drawn between the north and south poles. Okay, so I want you to imagine North Pole, like where Santa lives, to the South Pole, where the penguins live. Okay, meridians are the lines drawn from the North to the South Pole. Each one of those is numbered, and each one of those is numbered according to a system which is called longitude. Okay, so if it helps you remember, they're long from north to south, long from north to south, and the lines start at 0, which is the prime meridian, and they go 180 degrees to the east or west longitude. So 0, the prime meridian, and they go 180 degrees east or west. Now the parallels are the arcs that are drawn parallel to the equator. And you remember the equator because it's where Ecuador is, okay? And so the equator is also 0. By the way, these are latitudes, flatitudes, flat, lat. They are like the rungs of a ladder, ladder. So they go up and down like the rungs of a ladder. Okay, so remember longitude, they're long from north to south. Latitude, they're like the rungs of a ladder. They go up and down, or they climb like a ladder. So 0 is the equator, and they go 90 degrees north or south. So they're going to go up to the North Pole and down to the South Pole. Okay, I'm going to stop here, and we'll pick up in just a sec. Maybe.